Then we've come to the very interesting section called object detection. So a lot of the revolutions or a lot of the innovation right now has moved from classification to object detection, and some of the key drivers have been self-driving cars. So what self-driving cars need is that besides just saying, hey, there is a pedestrian on the road or there's a traffic signal on the road, they actually need the position there. Self-driving cars is one of the bigger ones, but people then started using this everywhere. There are a lot of applications today that are trying to leverage the capabilities of models today. So what objection detection does, it identifies objects in an image, like what classification was doing. It also localizes the identified image. By localizing basically means it says what is the position of it. And it provides a bounding box for the detected objects. Object detection, it means that you have to be able to detect multiple types of objects in the image, and the objects can be different types or can be the same type. And all this has to be done by object detection, and today's models kind of do that. Okay, so from classification, one of the ways in which people thought you can do object detection was to take a small section and then run a CNN in this particular area and identify objects that are there. That was one of the ideas that was done. So the idea was, let's just keep sliding this all across incrementally, very much like a filter. And then you run CNNs, you change the size of the sliding windows and change the aspect ratios of the sliding windows, use large ones, use small ones, and collect data from all that. And what you would get is you would basically get multiple predictions. And then the multiple predictions can then be merged to give a final prediction. So this was one of the ideas that was said. At first, as you can see, this is extremely time consuming because this required you to run a lot of convolutions separately. So this really didn't take off too much, but there were certain insights that people have made. It's so if you can see, running a step like this is very much like running a convolution layer. So what people figured out is that even deliver a sliding window architecture by basically running multiple filters, so large lot of filters, and each of them would be giving you different predictions. And so you could kind of do a sliding window in a single convolution by just running a lot of these convolutions in parallel, by stacking a lot of these filters up in parallel and doing it. And these ideas have kind of been used in a lot of models. So now we started talking about how to represent bounding boxes. So the critical architecture of doing bounding boxes was to have define the origin 0 0 at this point and the W and H at this point. What it does is you define a minimum X and a minimum Y and a maximum X and maximum Y, and that is a nice bounding box. This is quite widely used in TensorFlow object detection models, and which we were looking at. The other method was to use the midpoint and the height and width. So you define a midpoint for it and the height and width to define the bounding box. And object detection techniques like YOLO use this methodology. Both of them are sufficient to define boxes, and both of them use only 4 parameters. There's no reason why one is better than the other, and both of them deliver the same amount of information by using the same amount of memory, but different models or different frameworks have taken it. And in some ways you can see that a lot of frameworks today that do this, because there's still a lot of flux, a lot of development happening, and therefore there's still not too much consolidation that has happened in object detection. This is still a bit of a wild west like scenario still running. So a lot of the models that are one of the types of models that are very popular in this space is called a single shot detector, which, as the name says, was supposed to do detection and localization in a single pass. They call SSDs. And so what it would do is that it would give you a result like this. So identify the objects, give you probabilities and bounding boxes all in a single pass. There are SSDs and YOLOs, which are both basically single pass systems, but both of them work in a very different way. And so we started discussing what are single shot the architectures for SSDs. So the architecture for SSDs took the architecture at of convolution neural networks used for classification. So in a normal convolution neural network that's used for classification, we could break it up into two sections. One was called a backbone or the base layer, and a head. So for typical classification layers, the backbone were all convolution layers or max pooling layers, and the head were dense neural networks, which kind of in the end just collapsed all the information that's been collected by the convolutions to finally give class probabilities. So what SSDs did is that they started using again a backbone, but they put what is an SSD head on it, and so in some ways the instead of just dropping all the information, the ssd head would start extracting the bounding boxes and the class confidence. So they took normal layers and they just changed the heads. That was what it was done. So this is like an architecture how it looked like. Normally this would be a convolution, this would be an ssd head, and what this would do is basically convert that all to just cnn's, and in the end you would basically get results that includes the bounding boxes over here. So some of the things that people had to make sure is that, so you had new models, and so while at the training task itself, you just could not give images and labels. So you have to give images, labels, and bounding boxes. You had to give all of them. So the whole system that people had done till now had to change a lot. Also, it meant that the way we looked at losses during training had to change. So, typically, while training, all we cared about was this classification, cross entropy as the loss metric. But when the people started building object detection models, they started using more different types of functions. We can call them composite functions, which huge paths of classification and localization. Typically, a lot of the models look at classification loss as cross entropy, and localization loss as basically the difference between the x min y min. Sometimes some look at it as an absolute one, and some of them actually look at it square values also. Both of them are quite. Will weights be associated with min coordinates also? Yes. So min coordinates are basically just extracted out of the convolution. So there are. So you should remember that all this is finally coming out from the convolution neural network. So the weights. So whatever the internal representation is, it it basically has to look at both classification and the x coordinates, min x coordinates, min y coordinate. It has to look at both of it. So the weights would be a different kind of weights than what was being used for classification only. So that's why we can't just take a classification model as is and just say that, hey, now you just give me the boxes also. You can't do that. It's you have to kind of do it from scratch all over again. In principle, what you can actually do is you can actually kind of build a model, a Keras model, and you can create a head on top of it. Or actually, as like we did, you can just change the head, make a different layer that returns you, besides the probabilities and the class, a set of parameters. You can actually build it. It's doable, but it's obviously one of the first things people tried, and people have made a lot of progress. It's actually doable. You can use a Keras model. You can change the head, and you can do it yourself. But it's not as you would as it as accurate as what we can get with the latest models. People have already done that. Okay, so Ashwini Sahani says, can you explain it again at how it identifies a specific object to make the boundary as it is like an RGB image for an object? So what you have to understand is that now even training, so previously the input just had images and you basically had a label associated with it. And that's for classification. So this is input while training. Okay, this is while training. And while training for object detection will require the image, labels, and bounding boxes. So we will see an exercise later which will show you how this is done. So hopefully it'll become more clearer of that we actually feeding more information. But then we did training for classification. We have to feed in more information, and the input also looks different. And therefore the model gets trained to do both. So you train it itself to do both. You train it besides to do classification, you also train it to do object detection. And this it looks a little much like those complex models which we built in custom models, which where a model can also do classification, where a part of it can also do something else. So it's using those techniques internally to do that. People built that. As I said, this is still being changing almost year on year. There's a new model that's coming in that beats the older ones. and the architectures are changing. Everything is just changing. But bottom line is that to train all of them, what you have to do is you have to give them images, labels, and bounding boxes. You have to do all of that. Right. So we were looking at SSD. So what essentially says that SSDs, so basically after you drive it through a base network and the top head, it basically is capable of extracting bounding boxes and predictions, bounding boxes and predictions. It does both of it. And what we were looking at was an example. Right. So our first exercise was kind of try to do is what we did was we showed how to do we were doing the SSD. The model which we used was SSD Inception. So essentially, it's the Inception, the GhoulNet backend with an SSD head. These models are available from Google. I I gave a link where you give the and how it's implemented with OpenCV. The TensorFlow implementation was quite complicated. The OpenCV implementation is a lot easier. So what we need to so typically you get weights and config. Config is like you could say the graph, and weights is like actually the values that the weights of the model. So both of them are come separately. They can be added together and to build the model. And we took an standard image, dining table image, which I had. We looked at the shape of it, and then we started enabling processing. The first part is basically making into a format that's compatible with OpenCV. And then finally, what we do is a forward pass. So a forward pass essentially gives us the results. And now, as I said, this is what the results would look like. There would be a class ID and a probability, and it's different from our previous classification neural networks is that it also gives us minimum x, minimum y, max x, max y's. It gives us all of, and it does again, as you said, they have to do multiple detections. So these guys do this models do about 100 detections, and for each of the 100 detections, it gives you the class IDs and probabilities. Typically, the highest probabilities are the highest values, and the lower probabilities go low. To the box, we could see the box looks like this. So these are the 100 detections that have been made, and this is the array that contains this information. The index 0 is always 0, so it's a don't care. And then we looked at so since we did 100 detections, what we got to do is we have to run a loop around it, and we do a loop around it and then go through this our last index over here. So index 1 is class ID, index 2 is confidence, which is the probability. And so you could set a different confidence depending upon your application. And so a lower application would give you more detections, which often could be wrong. And setting a high one would give you fewer detections, but they'd be more correct. That is the whole idea. Also, that the output of this DNN gives you normalized minimum coordinates. So that has to be multiplied by the actual height and width of the image. And we also had done something interesting to just make sure that we have boxes for different colors for different classification for different tasks. And we kind of put the whole thing and did an output. And this is at a very high, I set very high. So this one just gives me 0.9. I showed you yesterday with different confidence layers, and you could see more different ones. So I'll just repeat that one more time. Like if I go to something small like 0.5, but please note that I have to read the image again. So I changed the probability, and now it's got to give me more detections. So this way you can set values that are what you're most comfortable with. Cool. So that was how we run object detection with SSD models on an image. The class, a lot of people are interested on how can we do this on video. So a video is nothing but a frame, is basically a stream of images. That's what it is. It's basically a stream of images. So in principle, whatever we do here can be done on a video, except that you have to run it frame by frame. Okay. So yes. So typically you have 30 frames in a video, 30 frames per second in a video. So every time so basically you've could be 30 images that are moving quickly. and that gives us the video. So in 1 second, we see 30 pictures, and that gives us a sense of continuity. If somebody so when I was in school, you were told that the minimum requirement is at least 10. So if you at least have 10, then you can see some continuity. 30 just ensures that we see moving images, and that's what this is. So you can quite easily do video processing, and I have given you the code to do how we do video processing. So what we do is, besides doing video processing, we're going to save the output of it. So because I'm using a notebook, and on a notebook doing video is a little difficult, so what we're going to do is we're going to create the output. So this is how you would create the output. Create an MP4 or an AVI also, and we're going to just do that. So I have already put one particular image, the video which we will use, called overpass.mp4 on CXL data. So this is accessible to everybody. So you don't have to save it in local database, because that becomes a problem over a period of time, is that the amount of data you keeps increasing. So what we've got here is we've basically going to first calculate the total number of frames. So there is a function, inbuilt function with CV2, that can give you the total number of frames. So you can use this function to do that. So this one is basically creating a video stream first, and this function then gives us a total number of frames, because we're going to iterate over it. Okay, so by default, I'm going to use something called IMUtils, because calculate the FPS, so the actual frames per second of processing, which is a very important metric. So we will be looking at this metric, and we just have to demonstrate how long it takes. So typically, okay, so this one would do everything. So what we do, so I'm not going to run it right now. If you run it, you will see that it takes a long time. I will run it on a smaller set of frames. I'll first explain to you what we're doing. Okay, so I'm importing this particular activity called FPS, which will help me calculate the effective frames per second of my processing. Okay, so ideally, what people want is 30 frames per second. You want to do 30 frames per second if you want to see this be running smoothly. And as you will see, it's not possible to get 30 frames per second with this model on this hardware. So that's a concern. So these are things which people are still working on. And the way this works is that now what you need is, you just can get the frame by using videostream.read, and the frame is basically an image. So you would basically keep getting 30 frames for a second of video. And then what you would do is, you would do exactly the same things as we did before. We would convert that to a blob, which is the internal representation of the image, and we would then do a forward pass and do exactly the same thing. Class ID, we would iterate across these boxes, across class IDs, setting confidences. So I set a very low confidence, and I had run this. And what you could do is, you could do an FPS stop, and you say, give me an FPS. So on this, what we got is, we got frames of 1.59. That is very, very slow. So it takes about 45 seconds to process 1 second of normal video. So that's one of the reasons why people need GPUs and high performance computational stuff and better models to do all this. Sometimes what people do to use it on low one is to kind of do process fewer frames. So skip a lot of frames if you want to do it live. So that's some techniques which people do. Anonymous attendee. If we want to detect only one particular thing in an image, then we train a model with only that particular class or label. That's correct. If you want only a particular thing in the image, or you can train an optimized model that just detects that one thing, and that would automatically give you improvement. So you can even just run classification, the classification once you're doing object detection, but you could be doing classification also, for example, or doing something more complicated. So I've already run this, and I have the model already. So I ran this with a very low accuracy, and it kind of gave a lot of detections, a lot of fake detections also. It sees bananas in some places. It's seeing cars and buses exactly over here, but it's seeing a lot of vague things also. So the model I've read is using Inception, and I'm basically getting an output directly. What I'm saying is that, so it's kind of inside it already. So Inception is a part of the model over here, and it is running in the forward pass. So whenever I do a forward pass, I'm running Inception and SSD on top of it. Error showing the last cell. Yeah, basically you have to install IMUtils. So IMUtils is what's missing, and this has to be installed. And typically after you install it, you may have to restart your kernel to do that. But you would have to do this only once, and after that, that would work. And if you run it, this will take very small. But if you want to run on extremely small or you want to see fast results, what you can do is you can run on just say 30, so just 3 seconds of video. Okay, and you can run it on just 33 seconds of video. That'll be a lot faster. So right now I've said that only frame count is 90. So I'm going to run it only on 3 seconds of video. That still takes some amount of time, but it takes in orders of minutes. Right now we are kind of we are assuming that things are working. One way to test if things are actually running is, so I'm saving output.mp4 over here. So if that is updating, that basically means, and it's already reached about 1.5 MB, 0.31 MB. So you see this is increasing. So my output.mp4 is kind of building up. So anonymous attendee. So we can detect close and open lanes with this. Yes, that's correct. You can train anything and you can detect open, you can detect uh, lanes, you can detect the light type, you can detect people, you can detect animals, etc. Whatever you need, you can do that. So this is the amount of time it takes to run this, and I got a much faster frame rate right now. I got 0.851 for some. So what I've done is, basically what I've said is what we're doing is we're looping across the entire frame. So by default, I was saying that frame loop it across the frame, but loop it across the entire frame, all the frames. What you can set is you can set a lower frame count by saying that only if the frame counts is less than 90. So typically we have 812 frames in this current video. So what I've said is that don't go through all the frames, go through only a part of it, the first 3 seconds of it. This is so first, so 3 seconds is 90. As so I think you said that 1 second contains 30 frames. So 3 seconds would contain 90 frames. So you could change any number there and you could get it. I think you can use them directly. You just need this one small minor change in the config file. So this most of it is exactly the same, and I have given the link there. So there are again a lot of these models are available in Model Zoo. I think this link has changed now. Anyway, this link is changed because this was for the TF1 TF1. That recently they have also released something called TF2. So typically, like if you were running without OpenCV, the code would look like something like this. Okay, this is actually TF1, and it would give you something like this. And these are some models which they've taken already and they have given, which is what I've taken. And some of these models require this minor change to be run, and then you can use. So this is what we have used over here approximately to run. We are using TensorFlow API, or models that have been created using TensorFlow is what's being used to run this. And this is just with OpenCV, it's easier. And I'm introducing OpenCV largely so if you want to do video, etc., it's much more complicated to do it without using OpenCV. You anyway have to use OpenCV or some weird tool otherwise to create these rectangular boxes and write on top of it. So it's anyway better to use OpenCV. There's a question from Avinash Saraswat. Is it possible to detect contaminations in fluid getting poured into the tank? It is possible. You would require very proficient camera to be able to get that, but in principle, it's possible. So as I said, if you want to use the standard flow, this is the standard flow. This also kind of works. This is a TF1 object detection. So very recently they have released, as in like very recently they released TF2 object detection. Kranti asks how you got to know which is the new release, etc. Because I'm reading about it all the time. That's why. So that's why the only way is that nobody tells me. You have to kind of keep reading about it. Oh, I thought I changed the threshold. Apparently, I didn't. Yeah, but you can change the thresholds and you can see a different set of things. So Let's run at 0.5. 90, it'll take approximately 90 seconds to. That is how you restart the kernel. You get to kernel restart, clear output. And so after running pip, so you have to run pip install first. You have to run this first, and then you have to do the restart. Ashwini Sanis, can you please give an example except Facebook where object detection is being used? So object detection is being used in cars, in self-driving cars. Object detection is getting used big time. People are using this for processing CCTV feed to identify traffic violations. People, this is something which we're kind of doing in some ways. People are using it for detecting theft in supermarkets. People actually use it even for analysis of medical images. For example, some people take medical images and then count the number of red blood cells, for example, in that particular image, and that also uses object detection. Object detection is being used in a lot of places. So to see the output video, Avinash, you can't see the output video over here. You just download the output video. So to download the output video, you go here, you click the image, you choose it, and click on download. You will get it. Okay. You can download it here. You may not be able to see it properly if you download it, and then you can see it locally. So Ritu Mehta asks, why is it that every time the threshold is modified, the picture needs to be red? So Ritu, that's basically because the way the code is written. So what we are doing is we have created something called IMG, the image, and what we're doing is that we have written the rectangle to this image, and then we have put this text. So what we're doing is then we are rerunning on that same. So please note, we are not changing. So if you just run this particular cell, IMG is the same. So you're getting the old IMG, the old object, the old image object. So what we technically need to do is we need to reset the original object. You can do that. I mean, a simple method over here is to run it all over from scratch again, or otherwise, basically, you can have saved the image, the first frame initially. G is over here, so you could say that initial frame, initial image is equal to img. You can run that, and then what you can do is you can set here that img is equal to initial image, right? And you can run this, and then you can show me the image, and you've got this. Now I can change the confidence to give me something much tighter to 0.9, and I can just run this. It doesn't work because I have to, because CV2 still has saved all this information. That's the reason. Otherwise, we have to basically clear out all these images. These rectangles have already been put in IMG. That is the reason. So object detection might also be used in space rovers for their path and satellite. Object detection is getting used in a lot of places. So a lot of things are just people are just watching what is happening. Inspection of inspection of assembly lines, where you have people watching. It makes a lot more sense to just train a computer vision model that to do that particular task, and it's going to do it much better than people do it, because the computer, obviously it's not 100% correct, but even people aren't 100% correct, and people are likely to get bored or make mistakes, and to a lesser extent. So actually, if it's a very particular task which you can understand very clearly, it's better. Computer vision tools and object detection is getting used extensively to do that. Is there a tool to create image inputs having object label contacts? We will come to that. We will talk about. So in the YOLO section, I have the section on training. So you can, if you this is uses SSD TensorFlow. I'm going to also discuss YOLO. In YOLO, we'll be doing a small. I'm also be introducing a training exercise, and we will see that. For SSD, for using TensorFlow, it uses a very different framework. We will not go through that in detail in class, but I can share you information where you can find. Anyway, so there is another one more something that goes ahead of object detection, which I just wanted to talk about and just show it to you also. So this is called segmentation. So what segmentation does is picks out the pixels which belong to that image. So there are different again. So these are more there are these are models that actually take a very long time to run. So what the way that runs it, it comes from a family called R masks CNNs. So the original idea of R mask CNNs was what they would do is that I think I have just an image. Kranti is asking where to apply this model and how means on which video, how to save a call video where this model can be deployed. Kranti, if you're asking about the segmentation, so segmentation is this so I haven't seen so much applications on video, but some people have used it applications for medicine to identify certain regions of lung damage, etc., very clearly. Other places where it's used, this is something which I had done a small project for some time. Is that we were trying to arrange look at damage on cars. Okay, so you wanted to assess how much area of a car was damaged, so you could actually detect dents by using such models. Because it not only say that hey there's a dent on the object box, it would actually give the pixels that was dented, and with that you could give a much more accurate assessment of how much area of the total car has been dented. So this is why segmentation is used. So I'm just introducing you to the concept of it and the idea. So because how segmentation came up was that actually so there was this so okay so there was so we were discussing how people did image detection, right? So as I said, image detection has some techniques where they did sliding windows, where they took small windows and they slided around it. So there was a technique called proposal or region proposal. So what region proposal was doing was used to study the pixels in an image, and using studying the pixels of the image and the way the pixels are changing it, you would give certain proposals that it said say that I think that there are objects in this area. So it would take this and it would study the pixel changes and give a proposal. And then on that proposals, people started running CNNs. So it was this is one of the older techniques, and so it again it you had to run a lot of convolution neural networks over and over again, which was made it slow. But what was possible is that because the pixel information was captured early on, people could use that to kind of identify the area of the image. Like for example, besides the wine glass, it gives this. And well, this guy actually identified this bottle over here, and you can see the pixels identified that go along with the bottle. So this technique is called segmentation. And as I was explaining, the model is that the way this kind of runs is that initially there are certain machine learning tools, SVMs, etc. Some and what it does is it studies the pixels, the way the pixels are changing, and gives proposals. Says that hey, this was possibly an object here, possibly an object here, possibly an object here. So it gives a lot of proposals. And then CNNs would run on each of these proposals. And then you would get a lot of results and they would all be merged together. So segmentation does things like counting number of objects of a particular shape, like in a grayscale image. It can count n number of objects with a certain color, say zero. Yeah, so there are ways you can use it. I'm just introducing you to the idea of it. That's all. And so again it's usage. Object detection is a lot more. There are many more applications of it today. Example, people also use it for an analysis of say satellite images. You have satellite images or drone images that you've got, and for example there is say you're going across a farm area and you want to highlight a particular area which is maybe it's not rectangular, also very obscene polygon, a very weird looking polygon, where the trees are infected or the crop is infected. So there you might be better off by giving something like a segmentation might be a better idea. So and then as I said, medicine also, for example, you have an X-ray of a lung, for example, and you want to highlight areas which maybe have tuberculosis. Just some thoughts. Or you would highlight the areas cancerous cells, the area that's malignant. And in that case, rather than a box, you kind of people want to be more particular about it. So these models have seem to be more accurate, but they're very, very slow. and very difficult to run on videos, and it's not used on videos. It's typically used for these very applications where you want to run something on a certain image. So the way it does is, yeah, it basically does multiple stages. It first generates a lot of proposals by studying the gradients and edges, and then you run classification on each proposal, and then finally uh, they do a lot of post processing and merge the results to your coherent results. So it's quite the same actually. It's a different model. Again, I've picked it up from the from the same place. So we are doing exactly the same things, loading the model using weights and config, converting it. So what is different about this model is that it, besides boxes, it also returns masks. Okay, masks are those areas. So the boxes are exactly the same. So you've got 100 detections, and in the detections you have the class IDs and the objects. What we've got in mask is that for each of the 100 detections, okay, please note, for each of the 100 detections, it gives you 90 polygons that are 50 by 50. So each of these 90 belong to a different type of class. Sometimes some of these probabilities are very, very low, so they just get discarded automatically. The mask basically have 100 detections. Each detection has 90 classes. So you have 100 detections, you have 90 classes, and what is actually shown is basically you get a 15 pointed polygon. The polygon basically has a confidence value. So again, a confidence. So if the probability of the object exists is very low, they will have a very low confidence value, and if it's high, it will have a very high confidence value. So that's how masks work. So the way we proceed is, again, you basically bound it to a bounding box. It's very similar to last one, except for we just have to study the masks, and then we look at pixel confidence, and we define a concept of an ROI, and it's pixels for. So it basically ROI basically means a region of interest. And what we're doing is then we are changing the region of interest to making it a blend of its actual colors and the color associated with the class ID. Okay, that is what we're going to do. So please note, as you see over here, what we have done is we to highlight the image here. What we have done is we have changed the pixel values to be a combination of the class color and the original image. So you kind of get a ghostish image over here. So the first part of the code is the same as we've seen before. We are iterating through the boxes and collecting the class ID, and looking at the confidence. If the confidence is slow, is high, then we are kind of making the bounding box. Then what we do is we collect the mask that corresponds to that particular class ID, because we know that that class ID exists in this box. So we look at the class ID there, and we what we do is, I'm printing the shapes everywhere. So what is basically done is, initially the boxes are much the dimensions are kind of normalized. They are normalized, and you have to bring it to the same size of the box, the bounding box, which is done over here. And we do the bounding box, and then we kind of have the shape. And what we do is, only if the thresholds are high enough do we create it. If else, we don't use it. So we throw out all the values of the masks where the thresholds aren't high. And then we have, what we've done is we are using that mask to highlight the area. This kind of highlights the area in the box. Then we created that blended image, and we print it together. Okay. Kranti, this is running. I just ran it in front of everybody. There's nothing wrong in this code particularly. There is, if it's this one, this is running. So you just can go here too and just click and use run all. It will just run. This will run all. It will run. This is just runs from by default. Okay. So I'll just again. This is some. So what this model gives, it basically gives boxes and masks. And what basically it's given is that for each detection, so like for example, over a detection over here, it's given these 4 points, which are the boxes, and then what it gives, a mask. So it'll give you 15 points. So 1 point over here, 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 1 point over here. It'll give you 15 such points, and each of these points, what it'll have a confidence value. So it'll have so whatever thread, it'll have a confidence value. So if it's a high confidence value, it's a low confidence value. So it'll get at most it'll give you 15. And so what we're doing here is it's only 15 points. So what we then really need to do is you need to make it into a region, and that's what the code there about does. It makes into a region, and at the end it makes basically once the region is identified, for that region the pixel values are changed. So what the pixel values then become is that you basically, in some ways, what you're saying is that you take the original picture and you adding the particular color associated with the class, you're adding to it a little, and you're blending it. That is what is happening intuitively. You're taking the original pixel, whatever the original pixel is, and you're adding some of the color that's associated with, say, wine glass over here, and that's how you change the color of the pixel, and you get this nice little look. So I'll just go through this again. We are doing the same thing. We're doing boxes. And so after finding the boxes, we get the mask. So the size of the mask is like 15 by 15, as I said. There's like actually 225 points on 15 by 15. It's 225 points we get. And we get 225 points. And then what you do is you basically, what you're doing is right now we are doing an interpolation and kind of filling it up, and then you've got a slide. Then what we end up having is basically you end up having 328 by 148 points. Okay, so what we have is basically just uh, we just have 15 by 15 points, which are endpoints. This almost becomes like an area, the entire area. And then what we have done is we have applied the threshold. There's no change to that. And then what we do is we apply that on the actual box to identify the actual shape. It's mapped to it. And so what we have is basically points. We have is points. Okay, so each point and 3 RGB values we have there. And then what we do is we change the values of pixels in those areas, and we in the end we finally just put it together. That's what this code is doing. Okay, anyway, this code is given. So in case anybody's ever interested in image segmentation, so segmentation is, again, it's as a part of computer vision. You'll hear the word, what is segmentation. So this is segmentation. This is how it happens. And what is done is, besides a box, you also get a mask. These things are called masks. They're essentially just polygons, and they can be mapped on the image. What does 1 comma 1 in the box shape indicate? 1 comma 1 basically means there's only one item. It's just the dimensions that are used to do this. It's always 1 and 1. These ones always 1 and 1. So it's essentially just 0 and 0. It's always 1 and 1. I think you can also use some of this if you're using I'm not sure if it works. Maybe in terms of you're doing batches or something, these values might change. An output of TensorFlow. Okay, this 1 comma 1 is an output of TensorFlow. So in TensorFlow, in principle, you can use batches of data. So I guess that is where it's coming from. Yes, this code looks a little more groovy, but essentially what it is, it's basically it's just taking the mask and just resizing the mask, applying the thresholds, and then mapping it to that particular region correctly. And then once you have the region, so when you have a region, basically you have the set of pixels in that region. And what we're doing is we're modifying the pixels, the value of the pixels in the region. So a lot of it is essentially for visualization, so that we can see it clearly. Yeah, so this covers segmentation. I was just introducing what segmentation is, as and how it happens. So what it is and what is happening at a very high level. and there are certain applications of it that I used. Okay.